Okay, the next topic is on random processes or random signals. From last time, we were looking at the random variables, and so an extension of the concept of random variables are random processes and random signals. So today we will look at the concept of what are the random processes and random signals. Then we will look at the Gaussian random processes and also how the random signals, when transmitted through an LTI system, do the stat- how do the statistical averages as well as the power spectrum density change. So, well, before we go into the concept of what are the random process is, so let's imagine this scenario. Let's say that we have a number of signal generators that can give 5 volts. Okay. And this is a factory that is manufacturing this type of equipment. Okay. So for each of the signal generator that is being produced, let's say that we set it to 5 volts in order to check the quality. And so when we set the 5 volts and then we monitor the errors from each signal generators, let's say all the way to n signal generators or all the way to the infinity generators. So, well, you can imagine that for each equipment that you produce, the amount of errors from the 5 volts, they will, vary depending on what you are looking at. Okay. Some may have large errors, some may have small errors, you know, some may have spikes somewhere, and so on. So, as for the manufacturer, they have to quantify this type of errors, or you can, in a way, you can say noise, in the equipment. So this noise from each signal generator, is not always zero because you always have some type of noise from these signal generators. Okay. So what is the random process or the random signals? So the random signals or the random processes is represented by XAT, where A represent the events similar to the random variables as before. And we also use a large X in this case to represent this random process. You can also sometimes write as X of t. Okay, the capitalized letter can be changed to small letter later on, but we'll keep it for now. The random process or random signal is an ensemble or a group of random variables at different time. Okay, and for each event, each signal generator represented by A1, A2, A3, A4, AN. This is can be for each of these term. So this represent the errors or the noise from each uh, signal generators that is processed. You can also sometimes write it as like this: x1t, x2t, and so on. Okay. So on the x-axis is the time domain, right? And on the y-axis, this is the amount of errors that are being monitored by the manufacturers. And we have to quantify these errors so that we can write on the side of the equipment, on amount of, say, root mean square error from the generators. Or if you want to produce more and more volts, do these errors appear constant, relatively constant on average, or they change depending on the amount of the levels of the amplitudes of the voltages that you generate. So that has to be uh, quantified. Okay. So random processes or random signals, they can be considered noise in communication system. because in communication system, noise is always random. Data signal can also be random. Random signals, it can be a function of time, can be a function of space. Imagine like image processing or images, and so on. If the random signals varies according to time, it is also sometimes known as stochastic process. So this is like the like jargon, when people say stochastic process. If the parameter that the random signals varies is not time, but is the spatial index, like images, then we don't call it stochastic process. Okay. So going back to the previous figures, what do we see at each time? At each time, let's say T1, okay, we can read out values from each signal generators that we are looking at. You can replace signal generators as different stocks, different brain signals from each person. You can think about it as the error from the brain signals, from the heart signals, or even some manufacturing output, like the amount of uh, amount of outputs that you produce, for example. So then at each time, let's say T1, we can get all this value, right, from each time. So what do we get at T1? We get all this value uh, from XA1 T1. This is from the first generators. We will get XA2 and then T1 and etc. Okay. X, let's say there are n of them. We can get xan and then t1. Okay. And all these, what are these? We can call this as a random variable x1. Okay. So at each time, what we have is at each time tk, we can read out these values xatk. You can say xaj, from a1 to an, or you can call it xk. Now, this is the random variable. You can plot the PDF and so on, right, at each time. At T2, then you get x2, which is another random variable, and so on. So meaning that at each time, you can get different random variables that come out, right? So that's why we say that random signal is in a way is the random variables that vary with time. So in order to understand this amount of noise from this equipment that you produce, you have to understand this big picture, which is the noise from each machine. And they may not be the same, right? In general. Yeah. Okay. And another example, random signal, you can look at xt, which is equal to carrier a cosine 2 pi f0t plus theta. Okay. So let's say at each time, let's say time t equal to 0. So what do we have? Notice that here I write the signal, the random signal, as the smaller case. So at each time, what do we have? We have xt. Also up here, I think the arrows is a bit screwed. Uh, Theta is a random variable. Okay. So you see that this term, there's nothing random at all except theta, which is the phase, right? It's the phase. So at time t equal to 0, what do we have? We have xt or x0 is equal to a cosine. T is equal to 0, so you have a cosine of theta. Okay. At t equals to, say, 1 over t, 1 over t0, where t0 is equal to 1 over f0, okay, where t0 is the period of the cosine. Then we have x of t 1 over t0 is equal to a cosine 2 pi times f0 times 1 over actually I need to say t is equal to t0, sorry, and then t0 is 1 over f0, and that's normal, right? Okay, but t0 is 1 over f0, okay, and then plus theta. So here we have that x equal to another time, which is t0. We get a cosine 2 pi, this cancel out, and then plus theta. Okay, so this is another random variable. Or you can look at t is equal to t0 over 2. Okay, then we have x of t0 over 2, which is at another time, is a cosine of 2 pi f0 times uh, t2 over 0, t0 over 2, right? But f0 is 1 over t0 in general. Okay, so we have like this. Then we have a cosine of this cancelled out, pi t plus theta, which is minus a cosine theta. Okay, so you see that at time t equal to 0, you have one random variable as a function of theta. Then for this one, you get the same one. Then it's okay. Then at this time, you get another random variable, okay, which is opposite from at time t0, t equal to 0 second. You know, you can play around with this, and even for random, just a carrier signal like this, carrier signal with the phase, at each time you will have a different random variable out of it. Okay, so in a way, this is a random signal. Okay, so questions. So in general, what are the means of at each time at t1, t2, and etc. Are these mean time dependent or time independent? Okay, it can be anything, right? But we hope that the equipment that we produce, the noise on average will be the same for each at each time. Of course, sometimes they drift. The errors may drift, after if you don't calibrate for a long time, like many years, then the errors may drift and you may have larger errors or more discrepancies, for example. But in general, within the calibration period, you would expect that each time, you would hope that each equipment that you produce, the amount of average noise is still constant or within the specified threshold. Okay. So these are some questions. Are the means M1, M2 all the way to, at all time, are they time dependent or time independent? Are the random variables between two time period, let's say T1, T2, T1, T3, are these random variables, are they correlated or uncorrelated? Okay. And also, are the random variables at the time difference, if let's say we look at the t1 and t2 or t1 plus t1 tau, we look at t2 and t2 plus tau. So at these two time, are the random variables from these two time with the time difference or time lag tau, are they correlated or not? If they're not correlated, it's quite difficult. If they are correlated, it means that you can do something about it. Okay. Okay. So now when we look at the random signal, it will affect the statistical averages or ensemble averages a little bit. So let's look at the mean. In this case, we're not looking at the mean of the random variables, but we're looking at the mean at time tk. At each time, what is the mean, right? So in general, the mean can be computed at each time tk can be computed from the expect because at each time we are having expectation of x at tk at a and then tk, all right, and then we can write it as xk. This is in a way at each time we have random variables, right? So the average at time tk is the expectation of the random variable xk, and for continuous domain you can compute from integration of xk. Let me put a small one because this is a value xk, and or you can just say x, just for simple integration of x, and then pdf of xk, x is the value and dx. Okay. And for the autocorrelation at a different time, ti and tj, or you can, in this case, we call autocorrelation because it's still the auto is the correlation of the random signal xt. Yeah, xt. Yeah, but at different time. So you can write this as xixj at time t1, ti and tj, or you can just say rx and then ti comma tj. Okay. Because at each time ti and tj we have different random variable xi and xj, we can just write expectation of the product of these two random variables. And in terms of the continuous random variable, you can write it as the integration of xi and xj. Let me put as the smaller case, multiply with the joint pdf. Okay. Well, I mean, you can similarly, you can define similarly for the discrete random variable as well, or discrete random signals as well. But then you replace the integration with the summation. Okay. So this would be the general way to find the mean at time tk, and also the autocorrelation of the random signal xt at two different times. Okay. So there are two types of random signals or random processes. We typically study the random processes or random signals that are stationary in terms of statistics. And there are two types. One is strict sense stationary random processes, which is in short is called SSS. In this case, all the orders of the statistical averages, they don't depend on time, right? Meaning that if you find the expectation or the moments at all orders, they don't depend on time or time difference whatsoever at all. And uh, another type of stationary random process is called wide sense stationary random processes, or in short, it is WSS. In this case, we only focus the first and second order of statistical averages that do not depend on time. Okay. If you remember last time, I mentioned briefly that when we look at the statistics of the random variables in general, we only look at the two orders on. Okay, and this is such a case. So in general, we will look at WSS mostly because we don't have time to compute the averages at all orders. Okay. Okay, so let's look at another example. Okay, let's say that we are given a sinusoid carrier with frequency f0, okay, where f0 is equal to 1 over t0 and an amplitude a, capitalized A. So this is from previously, this is a random signal. Let me say do I have enough space? So, okay, in case I have not enough space. Um, and the phase is uniform. The phase represent the scenario that if you transmit signal, which is a carrier from one antenna, And you have the receive antenna, on this side. Okay. So when you transmit some type of carrier, right? But then when you receive it, you don't know which phase you are receiving because there will be some delay when you receive it from the transmitter. Transmitter, I can just write as transmitter, and receiver, I write it as RCV, right? So the theta is quite random when you receive. Okay. So here we want to compute the mean and the autocorrelation of these random signals or random process. For the this uniform random variable theta, okay. Uh, Here we said that theta is between 0 and 2 pi because it's uniform. We can write it as a straight line, like I mentioned before in the past. Okay. And so what is the amplitude of this PDF of the theta? I think I should write the PDF up here, which is the vertical axis as f of theta and theta. Okay. And this is theta. Well, because we want the integration of f theta and theta, which is the PDF, over the existing period, the extending range of interest, which is from 0 to 2 pi. When you integrate total of the values, you get total probability, right? Total probability, which is 1. Therefore, the height has to be what? Okay. This is like a rectangle, right? If you integrate, it's like finding the area under the graph. So on the x-axis, you have the length of 2 pi, and you want the area to be 1. So the height has to be what? 1 over 2 pi. Okay. So we'll look from there. Okay. So why do I have so many space here? Okay. And then what else do we need to do? I guess that's about it. Okay. So let's go to part A. Part A, we want to find the mean of this carrier uh, of this xt, which is random signal. Okay. Or random process. For the random variables, I used to write in short as r dot v. Here I would like write it as r dot p dot, which is random process. Okay. So what is it here? We want to find expectation of this the random process, random signals. Okay, and it's a function, but the expectation is related to the random variable, not the time. So in here, we have a function of theta, but it has time and all that involved. It's okay. Don't worry. So we just, if you remember previously, we have expectation or function of any random variable. Let's say random variable y. Okay, we will just do integration of fy. Okay, let's say y is a random variable. Then we have, oh sorry, instead of using f, maybe I used g, a function, so you don't get confused, and multiply with the PDF of y, which is the base random variable. Okay. So similarly, we can do it here, but in this case, what is the random variable? It is theta, right? So this a cosine 2 pi f 0 t plus theta is just a function of the random variable theta. So we just do integration of a cosine 2 pi f 0 t plus theta, and then multiply with the PDF of theta and the theta. And on the previous page, theta is from 0 to 2 pi, so we can just write it like that. Okay. And then from the previous page, the PDF of theta is constant at 2 over 1 over 2 pi. Okay. Integration from 0 to 2 pi. Let me say I have more space on next page or not. Okay. And then I have this term. So what do? I will just expand it. Okay. I use the relationship of cosine of the sum of angle is cosine cosine and then minus sine sine. So I have a cosine 2 pi 0 t cosine theta and minus a sine 2 pi f 0 t sine theta and then d theta. Okay, so that's what I'll do. And then what I need to do is I just integrate each term separately. Okay, so I have 1 over 2 pi and integration of what? Okay, I integrate it with theta. So the t, whatever with t, uh, can be brought out. So I put here a cosine of 2 pi f 0 t. Okay, and I hope that you don't get confused when you have cosine and followed by 2 pi f 0 t. You don't multiply cosine with 2 pi f 0 t. The 2 pi f 0 t is an angle within the cosine, okay? And here you integrate from 0 to 2 pi. The only part that has theta is here. Okay, my pen, it gets a bit naughty sometimes when I write too fast. And then theta, okay. Similarly, I can do it on the right term. So I write it as a sine of 2 pi f0t divided by 2 pi and integrate from 0 to 2 pi of sine theta d theta. Okay. Well, from here, I'm not going to do more because the instead of integration, straight directly, I can just note that this is an integration of cosine within one period. Okay, and we know that integration of cosine within one period, you get 0. So this term is 0. Similarly, integration of sine within one period, I will get 0 as well. So this term 0, right? So that everything turns out to be, gives the mean of 0. Okay. So that's what we have. Okay. So we notice that the mean mx is constant at all time. Okay. So mx, I can put with parenthesis t like this, is constant at all time. Okay. Okay, for part B, we want to find the autocorrelation. Oh, I have a lot of space left. For part B, we want to find the autocorrelation. Okay. So we use this relationship. Previously, we have Rx of Ti, Tj, right, equals to expectation of Xti and then Xtj, right? But if Ti and Tj is separated by tau or time lag tau, we can also write it as Rx tau and expectation of x of t, let's say just any t, multiply with x of t plus tau, okay? And then see whether the results depends on the tau or not. Let me see if I have enough space here. Okay, maybe not enough space. Okay, anyway, but I think I can finish it here. So here we'll use this expression, the autocorrelation of the random signal at time lag tau, and I can write it as expectation of xt multiplied with x times t plus tau, okay? And x of t is a cosine, xt plus tau is also a cosine, but it has the addition of the tau here, okay? So two a's times together, you becomes a squared, right? Okay. So from here, we can use the relationship of a cosine, right? Cosine, I think, is the, I think you get this summation of cosine. I think summation of sine. Yeah, that's what you get. So you get expectation of a square multiplied with the sine of 2 pi f0 plus the, yeah, you get something like this. I think it's cosine. I'm sorry. Yeah, I think I made the, didn't remember. I didn't remember it right. So we have a, when we have cos A times cos B, we will get 1 over 2 and cos of A plus B and plus cosine of A minus B. Okay. So that will we get. So we get the summation of 2 cosine and one with addition of the angles. The other is the subtraction of the angles. Okay. So that we will do. Okay. So this is the property that we use. Okay. So from here to here, what do we get? So we have e square, e expectation of a square over 2 multiplied with the cosine of the sum of angle. So I have 4 pi f0t, right? Plus 2 pi 0 tau, okay? And plus 2 theta, okay? And then add it with the cosine of the difference of the angle. Then I have cosine of minus 2 pi f0 tau. And then theta and theta, they subtract it out. So that's what I have, okay? Well, if you go on with the expectation, like from the part A, similarly, for the first term, if you find this expectation, you have to integrate it with the integrate the multiplication of this term with the PDF of theta, okay? And it turns out you get something like 0 as well, okay? But then for the second term, what you have is you get expectation of a square over 2 and then cosine. For the angle, you can subtract or you don't subtract. It's all the same for cosine. So this is what we have. But then because in here, we don't have any variable that is random variable. So expectation of any values that are not random, you get itself. So you get a square over 2 and then cosine of 2 pi f0 tau. Okay. So here we notice that for the autocorrelation, Rx of tau also only depend on tau, okay, not specific time. Meaning that if you look at the relationship between the uh, random signals at time difference tau, no matter where you start, you always get the same autocorrelation. Okay. So I don't know whether I gave you the relationship here. Okay. So here, okay. What are the conditions for the wide sense stationary random processes? Number one is, I don't know, did I write it somewhere? Okay, maybe not. Number one is the mean at all time is constant, which is mx. Number two, you can find the autocorrelation of the time difference between two times. If the time difference, let me call it Ti and Tj in general. If the time difference between Ti and Tj is tau, we can just write it like tau. So it doesn't depend on where you start and where you start to look at the autocorrelation. You can think of like this. If you look at the noise signal in your equipment at uh, at present and the next 1 hour, what's the relationship? Similarly, if you look at the noise level in your equipment tomorrow at the same time and then the next 1 hour, what's the relationship? It shouldn't depend on the time you start looking at the relationship. If they're all very random, they're always very random, and so on. So it shouldn't be time dependent. So this is what we mean by the condition for the Weissen stationary random process. Okay, so in this case for part B, we will say that from A and B, we have that x of t is a wide sense stationary random signal. Okay. And why is it important to have this type of wide sense stationary random processes? Well, we will see later that first of all, it's quite simple in the case that your statistical averages for the two orders, they don't depend on time, right? So that's the first thing. And okay, let's look at some more properties of the autocorrelations. Number one is if you flip the time lag, you can think about the relationship of noise signal from now and the next hour, or from now and the previous hour shouldn't be different, you know. Okay, that's the first one. Secondly, there's a property called Cauchy-Schwarz inequality that says that Rx of tau when the uh, on the x-axis is tau is less than or equal to Rx of 0. Okay, here is 0, no? So this peak of Rx 0 always. Okay. Last time, if you remember, we look at the random variable, but at that time we defined the time lag. Is a time lag in a way similar. Yeah, it's similar because we look at different time lag, right? Different time. Okay. And I think there's another property number 3, but I don't remember. Okay. This is number 3. You can find the power spectral density in watts per hertz for any random signal. And in this case, I write it at gx of f is equal to the Fourier transform or DFT for discrete purpose, for discrete random signal. It's a Fourier transform of Ix tau. If you can find Rx tau for any Weissen stationary process, then you can find the spectrum this way. And lastly, so this one is important. Lastly, for the average power, Rx0 is just the expectation of x squared t. Okay, so this is an average. Rx0 is in a way equal to average power of the x squared t. Okay, of the random signal. Okay. In general, if you have strictly stationary OSSs, it means that you have a condition of the Weissen stationary. But if you have the Weissen stationary random processes, it doesn't mean you have the strictly stationary random processes. Okay, with an exception again, yeah, for Gaussian random processes, if at each time in the random signal you have this Gaussian PDF, we call it Gaussian random process. In this case, if you know that you have if you meet the condition of Weissen stationary, then it also implies strictly stationary condition as well. So for the Gaussian random process, strictly stationary and Weissen stationary, they are equivalent. Okay. Yeah. If you remember last time, there was another property, right? The relationship between random variables that one does not imply the other. At that time, it was the independence, right? Independence does not imply uncorrelatedness, except for Gaussian random variables. If you know that they are uncorrelated, they are also independent as well. Okay. And the last part, this is related to the PSD, power spectral density that I mentioned earlier. The unit is watt per hertz, right? It's a distribution of spectrum. So I can write it as g of x is equal to Fourier transform of Rx of tau. Okay. And what are the properties? Because it's a power, so gx of f is in general is greater than or equal to 0. Okay. And want to find, if you want to find the power, px is equal to integration of gx of f. Okay, this is for continuous from the uh, 0 to the bandwidth that you are interested. Okay. Okay, so an example, if you look at like the Gaussian random variables, Gaussian random process, and you also look at the white noise type, the white Gaussian random processes. You can just say like that. Yeah, you find that the autocorrelation with the time lag is an impulse with the value of the impulse is equal to, we can write it as sigma square equals to n over 2. Okay. And but of course in practice, you don't get like the actual impulse where it's supposed to get down to 0. You get some type of low values. Okay. And also for the PSD or the spectrum, okay, with the x-axis as the frequency in hertz, you get the PSD at the n uh, 0 over 2 watt per hertz. Okay, and this is the direct result of the Fourier transform of the impulse that gives you this type of straight line. Okay, but of course in practice when you plot it, you may not get the same straight line. You get some jagged line. Okay, so okay, and next one, thermal noise. When we look at the thermal noise, okay, it's normally considered as white noise because it's constant, has a constant amplitude of this power at all frequencies, right? Constant power at all frequencies. In general, it's infinite. It has infinite power. Okay, so in practice, if you receive your signals and it comes together with noise, you filter it with the bandwidth, say W anyway. Then the noise power becomes Pn is equal to, let's say this is white noise, then it becomes then 0 over 2 multiplied with W, right? This is for baseband. No, if you're looking at the band pass, then you'll get the N0W because the bandwidth is often twice of the baseband system. Okay. Yeah. And what are the N0? N0, in a way, because it's thermal noise, so it's a result of the electric circuit, right? Circuit components like RLC, for example. So N0, in circuit theory is related to the uh, Boltzmann constant multiplied with the temperature in Kelvin. Okay, next one. The last topic we want to look at is we want to look at how the if we have some system, that we send the random signal through this system. Let's say it's an LTI system. Okay, and at the output you get another random signal or random process, how does the mean change or how the autocorrelation change at the output? Okay. So in this case, we look at just a delay version. You have xt that comes in and it is added with the delayed version. Okay. So this is like x of t minus t. Let's say the delay is the one period or just t, This is not the period like a carrier. It's just a delay. So, okay. So let's take a look. So part A, we want to find the mean of y. So my of t, this is equal to expectation of yt, okay, which is equal to expectation of yt is xt minus t minus capitalized T, which is the delay. So this T, large T, can be called is the delay. Okay. Well, we can just expand the expectation because, like last time, is the linear operation. You can just expand and separate it, get something like this. Okay. Okay. Well, for the first term, this is just let me call it as the mx. Okay, and this is called mxt, right? And then minus this term, which is the average of the random signal with delay. Well, it's delay, you get the whole signal anyway, right? So the mean is still the same, mx of t, and you get 0, okay? Oh, also in here it says that the x of t is a stochastic signal, and let me add another condition that it is also a wide distance stationary stochastic signal or random signal. Okay, so mx of t is actually just mx, but in any case it's the same, right? You get 0. Okay, so that's part A. Okay, part B, we want to know what are the mean and the odd. For part B, what we want to know what are the autocorrelation of the output, whether it's still Y-sense stationary or not. So we just use the beginning formula that for any autocorrelation of random signal, we write it like this. I think in the last lecture, we computed autocorrelation often as well, but at that time we compute based on the time average or time domain. Okay? But here I mainly look at the statistical average. Okay. Well, from the previous page, y of t is xt and subtracted with xt minus tau. So let me put a bracket, parenthesis, so that is a bit easy to see. Okay. And multiply with yt plus tau. So the time of x also has to be added with tau. Oh, sorry, this is not tau. This is capitalized T. No? Don't get confused. And the large term is x of small t minus large t, and then plus tau. Okay. Okay. What we'll do is we'll just expand the multiplication of it, whatever in the parentheses. So we have two terms at the front. We have two terms at the back. Oh, I need a minus here. Then when we multiply together, we'll get four terms. So the first term will be x of t multiplied with x of t plus tau. Okay. I also will expand the expectation so that is a bit easy to see. And then Secondly, I have x multiplied with xt minus large t plus tau and with minus, right? So expectation of x of t and then x of t minus large t plus theta. Okay. And then go to the next two terms, multiply together. I have minus expectation x of small t minus large t or delay multiply with x of t plus tau. Okay, I don't think I have enough space. And lastly, this minus multiply with minus, I have plus, and then I use expectation outside. I have x of t minus delayed minus x of small t minus large t plus tau. Okay. So you may find that, oh, this is the very long, what am I going to get from here? So let's look at it. Let me change color so it's a bit easy to see. So this term, what is it? By definition, this is just the autocorrelation of Rx tau. Okay. What is this? This is autocorrelation of the time difference. You can use any one to be at the first term and subtract the other term because for autocorrelation they're all the same. So let me do it. I'll get Rx of, let me start from the t minus the last thing in the parentheses. Then I get t minus tau. Okay. This term, okay, similarly, I'll get, if I use the first term minus the second term in the parentheses, I get minus t minus tau. Okay. Minus t minus tau. And then Rx. And the last one, I'll get Rx minus tau or Rx tau, all the same, right? Okay, so what we'll get here is Rx tau, Ry tau is equal to Rx tau, but I have two of them, so I will write it as tau 2 times Rx tau. Oh, my pen is getting out of control now. Okay. Let me write slowly. So I get 2x to Rx tau, okay, and then minus Rx of t minus tau, and then minus Rx of minus t minus tau, but I can just pull out the minus, then I get plus. I get minus because the minus or plus inside Rx all the same, right? T plus tau. Okay. So you notice that the autocorrelation of the output y here, it only depends on tau, not the small t. Okay. So it does not depend on time t. Okay. It only depends on the tau only. Okay. It only depends on tau. Okay. So we can say that therefore from A and B, okay, y of t is also y sense stationary as well, because my is equal to 0 and ry tau only depends on tau, not the time. Okay. Okay. So for the last part of slides, I'm not gonna derive so much, but I will state the result so you can see. Okay. Because what happens is in the real system, the noise that come with the signals, it will go through many blocks as well, similarly to the received data signal. Okay. So if you have in general, if you have input to the LTI system. If the input is deterministic, the output can be computed from the convolution between the input and the impulse response of the LTI system or of the channel of the system. Okay. And this is just the formula for convolution. In terms of spectrum, for a transform y of f, you can just call spectrum, no? Spectrum is equal to x of f multiplied with h of f, okay? H of f is just the channel spectrum or system spectrum, okay? But then if x of t is random signal, let me change to red color so it's a bit easy to see. If the x of t instead is the random signal, so what happens? Well, we will look at the mean and also the PSD instead, or the power spectral density. Okay. So that's what important for the random signal. Okay. So lastly, let me show some results. I'm not going to prove it. Okay. So if you look at the mean, you get the mean of y is mean of x multiplied with h of 0. Okay. Where h of 0 is just h of f, where f is equal to 0. And for the autocorrelation of any random signal through the LTI system, it's a very long, actually, it's very long uh, proof. You get something like this. You get h of tau, convolution with h of minus tau, convolution of with the autocorrelation x of tau. Okay. And the important part is this. If you take Fourier transform, so what are you going to get? If you take Fourier transform, you get the PSD of the output random signal. Okay. This will be equal to channel spectrum square, the magnitude square, and multiplied with the PSD of the input. Okay. So this is the main important part. For the derivation, you can look at the slides. You know, it's quite lengthy actually. So let me conclude like this. So uh, so when we look at random signal through LTI system, we can compute the mean from these and the PSD as magnitude of the channel spectrum squared multiplied with gx of f. Okay. And we will be able to use it in the future. Okay, that's it.